All right, so we're doing 8-1. Excuse me. We're doing 8-1 and 8-2 all together. Yeah. Everything that I talked to you about today hopefully is a review from Algebra 3-4. Hopefully. If not, well, what can I say? All right, so a couple things. Just going to look at some vocab kind of stuff. So we're going to look at matrices and use matrices in order to solve systems of equations. Sometimes it's easier to just solve the system how I taught you in Chapter 7, and sometimes it's easier to use a matrix, especially if you're using your calculator. The beauty of the matrix and your calculator and the systems of the equations is great. But you won't always be able to use your calculator, so beware of that. So for your matrix, it's a rectangular array of numbers, real numbers. And it could be a square. Are you okay, Spoon? Yes, you are. And as I said, we will eventually use the system or the matrix to solve systems of equations. So that's our ultimate goal here. Some basic information on systems. We need to know how to name these. So you always name systems by their row first, and then their column. Okay, so think in terms, it's a good question. Think in terms of a spreadsheet, perhaps. Or think even more specifically Greek columns. Do Greek columns lay on the ground, or do they stand upright? Greek columns on a building, those nice fancy columns?
It's something that stands up straight.
Like, you know, on the White House, or like
Good point.
Lincoln Memorial, column goes up. The pillar.
Or if you think of Southern architecture, they have a lot of pillars or columns that are standing vertically. So columns are always vertical. Rows, think of laying down rows of cotton, or in a field, they're on the ground, right?
Think of like a row in a theater.
Okay. So this is your row. So right here would be a row going that direction. And then this direction would be a column. And it's easy to do. So if I were to name this one row by column, wouldn't I have two rows? So this would be a 2 with a big capital X, and then it's got 3 columns, right? So this is called a 2 by 3. It's really important that you know that you do row by column, because it's going to come into play when we multiply matrices. If you don't know how to name it, you're going to have trouble with multiplying matrices. So name this one B. How many rows and how many columns? 1 by 1. How about C? 2 by 2. And then D? 3 by 2. So that's easy, right? Once you remember row by column. And it's not alphabetical, so I don't know if that helps. And then we have these elements or entries. For instance, each item within the matrix is called an element, or it could be called an entry. And it has a specific directional spot, so to speak. So if I said find the element that's in the, or name the element that's in the 3rd row, 2nd column on D. 3rd row, 2nd column, what would you tell me, what number? -4. And it might show, for this one, it might show that the elements, oftentimes they like to use the letter A to represent an element. And they'll say, okay, it's in the 3rd column, 2nd row. So it's A sub 32, but it's not really 32. The first one is the row, the second one's the column. So A sub 32 is equal to -4. As long as you understand the notation, it's easy to identify what they're asking for. And so that kind of brings us down to name and position of elements. So this is a 2 by 2 matrix. So this is position row 1, column 1. So it's A sub 1, 1. Row 1, column 2, A sub 1, 2. It's not really 11, it's not really 12, right? All right, then a square matrix is just equal numbers of rows and columns. And which one above was a square matrix? C, right? And B also, correct? 5, a main diagonal. All that is, you go from the upper left down to the lower right. This would be called the main diagonal. These down below are called identity matrix. And if you happen to look at the main diagonal, what do you notice about the main diagonal on an identity matrix? They're all ones, right? The diagonal ones. Mike, can you put it back there so I can see that? And the last kind of bit of information, so to speak, is what's the difference between a row matrix and a column matrix? Well, first of all, on these notes, Mr. Gleason has them backwards. Does it make sense that a row matrix would have just a row, one row? Right? That's why we call it a row matrix. What is this? One what? So this is one column. So it's really not a row matrix. This is a column matrix. And this is one row, so what's it called? Yeah, you need to change that and call that a row matrix. And I'll ask you that question on your test. Make sure you have it clearly determined in your brain and that you study that. Yes. This has 3 columns, but one row. Because remember, rows laid down on the ground, columns go straight up, vertically. This one has 1 vertical column. This has 1 horizontal row. Rows are horizontal, columns are vertical. All right, so flip this to the back. I mean, your homework really shouldn't take you too horribly long. There's a couple of things that will take you a little bit of time. But you know, one of your questions just asks you to write the augmented matrix to the system, or they'll give you the augmented matrix and you have to write the system of equations. So all we have here is a system. All you have to know is we can take this system and tomorrow we'll take the system and do something with it. But for right now, all I've done is removed. First of all, wherever the equal signs are, there's a line there. So this line here, typically in your textbook, you'll see it as a line like this, I believe. It's your augmented line. And all it does is it separates the answers from the variable terms, the constants from the variable terms. You notice over here that these are all the variable terms, right? And these are the constants or the answers. And all I've done from here to here is remove all the variables, and I've just written the coefficients. So this right here, this is a coefficient matrix. It's the same as the left side of this augmented matrix. And all it is the coefficients. And then, of course, take out the equal sign. Here's your answers. And I'll show you what to do with that tomorrow. But you need to know how to write it. Then we're going to look at mainly operations. Addition, subtraction, and scalar multiplication are really simple with matrices. And you might have done those in Algebra 1 and 2 or in 8th grade math. You definitely did it last year in Algebra 3, 4. So I've got 4 different matrices. They're all 2 by 2s, right? Correct? Well, first of all, what do you remember about adding and subtracting matrices? Is there an important rule that you have to remember? They have to be the same rows and columns. So I cannot add a 3 by 2 with a 2 by 3. Even though they have the same numbers in there, they have to have exactly the same rows and exactly the same columns in order to add or subtract them. Not so with multiplication. We'll look at multiplication later, and I'll show you, how to determine whether I can add those. So for this first one, it says if A equals B. So look at A and B. We're just going to set them equal to each other. So you might want to write small. So that you can fit some stuff in here. So I'm going to take A, which is vertically I'm going down 1x and 2, 4. I'm just going to set that equal to matrix B. So matrix B is vertically 1, 5, and then 2y. Now what this says is that each element or each element in the same position in each matrix are equal. So this is the 1, 1 position, and that's the 1, 1 position. First row, first column, aren't they both 1? Okay, aren't these both 2? So what would x be here? All right, so that's easy. X is equal to 5, and then y is 4. So for something like that, those are easy. Then we're going to find matrix C plus matrix D. Are they both the same order? Yeah, 2 by 2s. So we're going to take C, which is 5, 7, and 6, 2. And I'm going to add to that D, which is 4, 5, and 3, 4. You might have to kill a tree while doing your homework tonight. Definitely tomorrow. You'll be definitely killing trees tomorrow. So then you need to add the same positions. What's 5 plus 4? 9. 6 plus 3? 9. 2 plus 5? I'm sorry, 7 plus 5? 12. 2 plus 4? 6. Done. So this is my answer. Now we're going to multiply by a scalar. All this means is take matrix D and multiply everything in it by 5. So I'm going to take 5 out in front of the matrix. Matrix D is vertically 4, 5, and then 3, 4. So I'm going to multiply the 5 to everything. What's 5 times 4? 20. 5 times 3? 15. 5 times 5? 25. And 5 times 4? 20. So that's my answer for that one. You do have to be careful with subtraction. If I'm taking D minus C, which they're both the same order, 2 by 2, so I can do the subtraction, I would really rather take D plus a negative C, wouldn't you? I'm going to multiply every element in C by -1. I'm going to just change their signs. So if I were you, I would take D, which is 4, 5, less in your head, more on paper, kill a tree. You're less likely to make an error. So then I'm going to add the opposite of C. So here's C, -5, -7, -6, and -2. Now I can add those together. So 4 and -5, -1, 3 and -6, -3, 5 and -7, -2, and 4 and -2, +2. So those are all pieces of cake, right? All right, well now we're going to get to multiplication. I'm going to show you how to do it by hand and on your calculator. So this will take a little bit of time and some space. So we're going to start with something easy, a 2 by 2. We're going to multiply A times B. And then we're also going to multiply B times A. I'm going to prove to you that A times B does not equal B times A. Normally a multiplication isn't multiplication commutative. In other words, I can multiply in whatever order I want to. What's 3 times 2? 6. What's 2 times 3? 6. Sean, are you awake?
Yeah.
Okay. So with regular numbers, it's commutative, but with matrices, not necessarily so. So let's go ahead and figure out what we're going to do. So here's your A and your B. This is the ones that we're working with right here. So when you're doing this, you're going to take, you can think of these are actually called vectors. So here's this row is going to get multiplied to this column right here. You take this row, and I'm just going to turn it this way and multiply it to that column. It's really a dot matrix. If you think of this as a vector 1, 2, and this is a vector 5, 7, then we just take 5 times 1 and 2 times 7 and add them together for a dot matrix, or dot multiplication, dot product. That's all we're doing here. So save yourself some room. Write it small. We're going to take A times B equals. Because these are your notes. So in element 1, 1, I've got to use row 1 and column 1. Does that make sense? Element 1, 1, I'm going to use row 1 and column 1. And because this is a 2 by 2, and this is a 2 by 2, the inner two numbers in the order must be the same. These outer two numbers can be different. But the inner two numbers absolutely positively must be the same. So if I had a 2 by 2 and a 3 by 2, that wouldn't work. But I could have a 2 by 2 and a 2 by 3, and that would work. The inner two numbers have to be the same. The outer numbers are going to give me my resulting matrix. I'm going to end up with a 2 by 2 because my outside numbers are 2 and 2. So I know I'm only going to have 4 elements in this entire matrix. So I'm going to start off with 1 times 5, and then plus, we always add them in a dot product. And then I'm going to move on to 2, and I'm going to multiply it with 7. So 2 times 7. That gives me my first element. Then I want to go and multiply the first row to the second column. I want the first row and the second column go in here because that's the first row, second column. I'm taking this and now I'm going to multiply it to everything here. 1 times 6. So 1 times 6 plus. Then I'm going to take 2 times 8. So first row, second column gives me element 1, 2. Then I'm going to take this row here. I'm going to take this second row, but I'm multiplying it to the first column. So it goes in the second row, first column here. So I'm going to do the dot product of 3, 4, and 5, 7. So I'm going to multiply 3 times 5. So here's 3. And here's 5. Plus. Then I'm going to multiply the 4 times the 7. 4 and 7. Then I'm going to do it again, but I'm going to take this row and I'm going to multiply it to the second column. Second row, second column belongs to element 2, 2. So 3 times 6. And then 4 times 8. You definitely notice a pattern. You can see the first matrix here, 1, 3, and 2, 2. And then you repeat this column here and here. And then you see here the first matrix being repeated again. The columns are 1 and 3 and 2 and 4. So you can, look at the pattern and figure the pattern out, or all I'm envisioning is taking this row and turning it vertical and multiplying it to that column. It's a spatial thing. This row turned vertical and multiplied to that column. That's what you're envisioning. The more of it that you write out, the less likely you are to make a mistake. And so I end up with, next one, 1 times 5 is 5, plus 2 times 7 is 14, 3 times 5 is 15, plus 4 times 7 is 28, 1 times 6 is 6, plus 2 times 8 is 16, 3 times 6 is 18, plus 4 times 8 is 32. And then finally, I can do my final addition. So this gives me 19. This gives me 2, 3, 43. That gives me 22. And this gives me 3, 4, 50. So this is my final multiplication of A times B. Do you recall that? Yeah. So it's not any more difficult with a bigger matrix. It's just more work, and you might literally have to take your 11.5 by 8 paper or 8.5 by 11 paper and turn it sideways and do your work sideways on it so you have more room. It's your choice. All right, so now I'm going to prove to you that B times A is different. So we're going to find B times A. So I'd like you to try that on your own. I'll go ahead and do the work up here also so you can kind of follow along and see if you're doing it correctly. And I personally, if I were you, I would rewrite the matrices because I'm a visual person. I would actually write B equals over here because I need to see it to do it. And for me to do it backwards really messes with me. But that's just me. So, many of you don't have to do that. Question? Madison, no? You okay? Yeah, so I'm going to take this row and I'm going to multiply it to this column. So I'm going to take that and turn it, essentially. Did I get the same matrices? No. So multiplication of matrices is not commutative. Now, of course, if I had the same matrix times itself, if A and B had the exact same elements in there, then it would be, but then you really are doing A squared, right? Or B squared. So bear that in mind. Okay, I'm going to have you write the directions on how to put it into your calculator, and then we're going to put it in the calculator. So as soon as you're done writing that, I'll put the directions for the calculator up here and have you copy those down. And then you can practice putting it in the calculator, but I'll also put it up here myself for you.
Do you already know how to put a calculator?
You can, yep. But if you don't, I'm going to give you the exact directions. So can I take this away? Yes, no? Okay, here's the calculator directions. So this is the first set of directions. So this is on your calc. You need to go to your menu and find matrix. Where might that be? Where's matrix? Say that again.
Second x to the negative 1.
Yep, if you look above your x to the negative 1 button, you'll see matrix up there. And then you'll scroll right to edit, and you'll input the matrix order. So because we're going to put in a 2 by 2, did you not have it on there? Where's yours? Oh, matrix, it has a button for it, yeah. So some of you have a button, an actual button that says matrix. So depending upon which TI you have, depends upon what you're going to do here. So you have to find your matrix button. Either look at your second function above the x to the negative 1 key, or you actually have a key that says matrix. Then you go in and you have to tell the calculator what the order is of the matrix. Is it a 3 by 2, a 2 by 2, you know, whatever it is. And then you have to put in each element. And you have to watch how it puts in the element. I believe it puts it in horizontally. And then you have to repeat it for your second matrix. So are you done writing that down? Can I scroll over for step 2? All right, so here's step 2. So from the matrix menu, well, you have to be out of the matrix menu. Weird but true, at least for my calculator. I don't know for all of yours. But you have to do second quit, make sure you're back at your main screen. Then go back into the matrix menu, select matrix A, then you'll press your times key. And then you go back into the matrix menu and select B. Hopefully put matrix A into matrix A and matrix B into matrix B. And then finally you'll press enter, and it should give you our first one. And then you're going to go back in and do B times A, and it should give you your second one. So I'll input this in a minute. Write down the directions. Because if you don't know how to do it, you'll forget. Yeah. No, just those two. Because believe me, on your SATs, if they're going to let you use your TI, this is great for doing matrices and for solving systems, because you can let your calculator do it. It saves you a whole ton of time, especially finding determinants and inverse matrices. There was only one on yours?
No, there was a lot of
I had one.
Yeah.
I had one.
Yeah. Okay, are we done writing this down then?
I think I had
Okay.
First one is
Okay, input it into your calculator. Where? Oh, well, yeah. It does say matrix. That's because I have a big and powerful brain, and I was writing a whole lot. I was thinking a whole lot faster than I could write.
I do that all the time.
sure.
Now, you might have something entered into your matrix already. You just have to change the order and re-input the values, and it'll change it for you. Uh-huh.
I promise I know this.
Did you see that commercial?
Might put it in. Let's go. Into your calculator. Yep. So input it into your calculator. Can I take this away yet? Yep. Okay. So here we go. So I'm into my matrix menu, and I need to go into edit. So I'm going to scroll over because I want to edit matrix A, and so I'm going to hit enter. And it asks me up here, it's blinking up here, so I need to put in my order that's a 2 by 2. So 2 enter, and it immediately changes the screen to a 2 by 2. So I need to fix my elements. For A, I want 1. And so it is going across horizontally, and so then 2, and then 3, and then 4. Then I need to get back out. Whoops, I don't know what I just hit. So then I need to hit edit again. I need to scroll down to B and hit enter. I have to change the order 2 by 2 and then put in my elements. B is 5, 6, 7, and 8. So now from your main screen, you're going to go back into your matrix menu. I keep hitting the wrong button because I can't see. And you want to hit just enter A. And see how it shows a little tiny matrix with an A there? That should show up so it knows that it's talking about your matrix A times. And then go back into the matrix. And you can either hit 2 or scroll down to 2. But you want to have matrix B. And then when you hit enter, is that what we came up with for our matrix by hand? Yep. So then do the commutative. So flip it around, matrix B times matrix A, and then enter. And so obviously they are vastly different. Okay? All right, so then flip that over. I've got a couple more things to do with you. So put your calculator away for right now. So then you have various properties of matrices. Although multiplying of matrices is not commutative, it doesn't matter what order. If I have 3 matrices that I'm going to multiply them, I could multiply B times C first and then times A, or A times B and then times C. I will get the same answer. What I can't have is A times B does not equal B times A. I can distribute either in front or behind parentheses matrices, and that will work. And then, although some of you might do B times A or A times B, when you add them together, they should still give you the same answer, theoretically. This is just a scalar multiplied into there. And then here's addition and multiplication. So it's a lot of the same thing. If I add 0 to a matrix value, aren't you still going to get the matrix? Okay, so you can explore some of these down below. And possibly in your homework. All right, so here we're going to use our algebra with matrices. So we're going to solve x in the equation. And then A and B represent those 2 matrices. So if I were to solve for x, algebraically, what would I do first? Subtract A, right? And so I would have 3x is equal to B minus A. Then what would I do? Divide by 3. So let's think about this. If I were to actually write it, because I would want to take the matrix B minus A and then divide everything by B. The answer in your book is probably going to look like this. Isn't that the same thing? So I really have scalar multiplication of 1/3 to that difference. Now I could distribute the 1/3 and then subtract them, but oftentimes that's going to give you a pain. You're not allowed to do this on your calculator. You need to do it by hand. So then we're going to take A times B. So x is equal to 1/3. And if I do A times, or I'm sorry, B minus A, don't I want to change all these signs here? Don't I want to do B plus a negative A? Right? So I'm going to change this to a negative, that to a positive. Well, there really isn't any opposite to 0. And then that's negative. Then I'm going to add those together. So negative 1 and negative 3 is negative 4. 2 and 4 is 6. 0 and 2 is 2. Negative 3 and positive 1 is negative 2. Now does 3 divide into all of those evenly? Notice you might have some ugly fractions, that's okay. So negative 4 divided by 3 is negative 4/3. If on your calculator you happen to be doing something and you get a fraction, it might give you a decimal. Do you remember how to convert that to a fraction? Go to Math, enter, enter, and it'll change your decimals to fractions. Hit the Math button, enter, enter, and it'll change it. 6 divided by 3 is 2. 2 divided by 3 is 2/3. Negative 2 divided by 3 is negative 2/3. That is what x is. Then I want to start you on a couple of things. Question? You okay? Okay. So then on the back of this blank back of this page, let's talk about our knowledge of row echelon form, kind of, and using that for matrices. We're going to I'm going to start to get you to think about how do you get an identity matrix. Remember that matrix on the front page where the main diagonal is all ones. So write this. Elementary row operations. Here are some various things that you might do. You might interchange 2 rows. And what I mean is the rows switch places. Something else that you might do is multiply a row by a non-zero constant which would be scalar multiplication. Or 3, you might add a multiple of a row to another row. So I'm going to put an example of an original matrix. And we're just going to start to think about an identity matrix and how you might start to change. We're just going to change the first column only. And so we might start with vertically 0, negative 1, 2, 1, 2, negative 3, 3, 0, 4, 4, 3, 1. So I'm going to concentrate on this first column right there. That first column, I want to get 1, 0, 0, because I want to get a 1 on my diagonals. Even though we have an extra diagonal, we won't let that bother us for here. So do I have a 1 here? No. Can I use any of these to get a 1 here with what I currently have? Or even a negative 1? I can switch these two rows, right? So step 1. And we're going to call this row sub 1, row sub 2, and row sub 3, just for naming purposes. And so I'm going to take my new matrix, and I'm going to switch. I'm going to put the second row up top, and the first row in the middle. I'm going to leave the third row alone. So all I did here is I switched. This is row 1, and that was row 2. So I just switched them around. Interchanged. Row 1 and row 2. Step 2. So I almost have a 1 here. What can I do to make it a 1? Say it really loudly. Multiply the whole top row by negative 1, right? That would be scalar multiplication. So I'm going to, now this is, by the way, now row 1. I'm not going to keep, because otherwise it could get confusing. So this has now become row 1. So we're going to take negative 1 times row 1, row sub 1. And I get the following. 1, negative 2, 0, negative 3. And the second row stays the same. Well, all the rows stay the same now. And all we did was multiply the new row 1 by negative 1. So now I have 1 and a 0. I need to make that into a 0. So we have to get a little tricky. What shall we do for our last step? Combine a couple things. What might I be able to do to something up here and then perhaps add it to that? I can multiply this row by negative 2 and add it to this row, right? So we're going to take negative 2 times row 1. We're going to add that to row 3. This times negative 2 is negative 2. Negative 2 plus 2 is 0. So it's creating my new third row. Oh, I guess this is actually going down here. Sorry. Bless you. Negative 2 times negative 2 is positive 4. Positive 4 plus a negative 3 is 1. 0 times negative 2 is 0. 0 plus 4 is 4. Negative 2 times negative 3 is 6. Plus 1 is 7. So the second row stays the same. 0, 1, 3, 4. And then 1, negative 2, 0, negative 3. So we multiply, well, we add row 3 to negative 2 times row 1. So then we got our first column of 1, 0, 0. So that's just manipulating rows by using row operations. We're going to do some more of that tomorrow too. Questions? We were just messing around with it. It's not really an answer. We weren't really doing anything final with it. I was just showing you how we could manipulate it for what we wanted.